Hey everyone, so this is the second slides and lectures dealing with entropy and temperature. So, continuing on with our discussion, I just want to make a few comments. So, one thing that we're going to make is what we call a fundamental assumption, basically, that everything that we're going to be discussing is based on the concept that when we have a closed system, which is what we're doing for a lot of these cases, that pretty much every possible state is available. So we had mentioned before about how, if we have I believe it was a 10 particle system, that there's about 1,000 plus possible states available. We're going to assume that every single one of those states is actually allowed. So it's not like there are certain cases that are just impossible no matter what. So that's the basic assumption. Now, what we mean by a closed system, remember in thermodynamics, a closed system basically means that there is no changes in external factors, that the system is not really going to be affected by things like a magnetic field, an electric field, a gravitational field, anything like that. And then things like the amount of energy in the system, the number of molecules, the volume, those all remain constant. Essentially, another way of phrasing it is that there's not going to be any sort of exchange of mass, of energy, of anything like that between the system that we're discussing and the outside world. And that the outside world has no bearings on that, on what's going on in that system. Um, so with the accessible states, as we said, this is kind of like a physical thing. Here, we're going to assume that things like any small changes in the energy is going to be extremely small. And same thing with the number of molecules, that again, in real life, we have to kind of make that distinction that, of course, there's going to be some changes in energy and particles, but we're going to assume that it's an extremely small change so that we can pretty much kind of almost ignore it. All right, so with probability, this is just a rehash of what we said before, but we just kind of want to state it again. So if we have something like G representing all the accessible states that we have, and we're going to assume that each one is equally probable, then what we can say is that the probability of being in any one single state would just be 1 over the total number of states. And then, of course, when we add up all these probabilities across every single one of the states, we should get 1. That's usually one thing that they sometimes call is normalizing the probability. That we'd want to make sure that when we do this, taking this probability and summing it across it all, we should get 1. And then, as we mentioned before, when we take an average of anything, whatever that property is, it's always going to be this weighted average, that basically we take the value at one point and multiply it by the probability, and we sum it across every single one of the possible states. So for the closed system where each of these states is equally likely, we basically end up getting something like this. All right. So we want to practice a question real quick. So pause video, work on this self, and we'll go over it in a second. All right. So this is that whole thought idea about the whole, monkeys typing on a typewriter, creating Shakespeare. Well, we want to actually see if that's what the probability of that is. So we can say that the probability of getting one single character correct is going to be 1 over 44. There are 44 keys here, so getting the one key correct would just be 1 over the total. Then what we want to do is getting all of the characters correct. Now we're assuming that there's no real difference between capitals and things like that. So what we're going to say is that we're going to have the probability of getting the first key is 144. The probability of getting the second key right after is going to be this times 144 again. So we're basically just going to have to multiply the probability of getting each key correct by the number of characters we need to do, which in this case is 10 to the fifth. So uh, this basically simplifies into looking like this, that it's 144 raised to the 10 to the fifth. The probability of getting one character raised to the number of characters we need to get, which is essentially 5.4 times 10 to the negative blah blah blah. They want us to get it in this order, so yeah, this kind of simplifies can be rewritten like that. So it is roughly on the order of 10 to the 1 negative 164,345. So the probability of getting Hamlet is really, 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 really small if you're just randomly hitting keys. Now here's the next part that I want you to work on. You could pause the video and work on this yourself, but really quick, I would recommend try to use unit analysis. Try to use the units provided in order to answer this. All right, so what we're going to do, we already know the probability of getting it. Now we want to get it, figure out the probability of getting it within the age of the universe. All right, so the number of keys that we need to type is going to be equal to, well, we know that there's 10 keys per second. So when we use this, we can say that within the age of the universe, each monkey is going to be able to type 10 to the 19 keys um, during the age of the universe. So that's the first thing that we want to state. Because we have 10 to the 10 monkeys, we're going to then multiply this to figure out how many keys had been pressed within the age of the universe. So the probability would just be the product of the how many keys we're able to press times the probability of actually getting all the keys right in one shot, and we end up getting this. Now, one really nice thing about these questions that give you the answers at the end is that you can almost kind of try to work backwards. I relate this to being similar to how a kid solves a one of those maze puzzles where you kind of start from the beginning, you start from the end, and you kind of work your way towards the middle. So you could do something similar by that, by like figuring out, well, what is the difference between this number and the probability number that we found before? Figure out that it's basically off by a difference of 10 to the 29th, and then think about how we can use the other numbers that were given to us in order to kind of, stumble towards the answer. Again, this is something that you can do if you're having a really hard time trying to figure out where to take the first step. All right. Now, one thing that I want to bring up is that there is another way that we can find an average of something, like an average value, without using this whole probability. And that's by considering a case where we have a large number of systems, all pretty much occupying one of the states that we're talking about. So, for example, let's say we want to know the average value of the the magnetic moments for a system that has a certain half spin system. Well, what we can do is just assume that there's a system that includes every single one of those possible states, where maybe there's three pointed up and one down. The first one's pointed up and the next one's pointed down, and then the last two are pointed up. You know, things like that. Like every single possible combination that we have, we assume that each of these systems has that, and then we just take an average of all of those values of those systems together, and what we'll end up calling that is an ensemble average. So you'll see what I mean in a second. A lot of times with the things that we're going to talk about in this class, it makes a lot more sense once we actually start getting down and dirty with it and doing something physical rather than me just mentioning it, which is one of the reasons why it's so important that you kind of try these questions yourself, but ultimately making sure that you're practicing them along with me. So we'll consider a case like this. You can pause the video, work on this stuff, and we'll go over it in a second. All right, so we have four particles and we have a spin excess of 2, and we want to know what is the total number of accessible states. Well, what we're going to do is use our multiplicity function to figure this out. So we know that the total number of particles is 4. We know that the spin excess is 2, which means the half spin excess is 1. So we're going to use this factorial because we have small numbers. We do not want to have to do that case where we have that e function. So, because remember, that's only for big, large numbers. Here, the factorials, we can easily do them even by hand. So the number of particles we have is 4 factorial. Then it's 3 factorial times 1 factorial. And that gets us 4. So there are 4 possible states that give us a spin excess of 2. All right, so these are the total. Would be what we consider the ensemble of this. So we have 1 down, 3 up, 1 down, 2 up, 2 up, 1 down, 1 up, 3 up, 1 down. Now the big thing is, if we assume that each of these particles are identical, then when we take the average, it's going to be the same. So the reason why we're doing this is because each of these particles actually isn't the same. So they kind of say that the dipole moment is d, 2d, 3d, and 4d. So it's going up by d each time. Now you might say, well, how do I know that this isn't d? Doesn't matter. All that matters is that one of them is consistently given the dipole moment of d, the second one, or one of them's given 2d, and so on and so on. So now what we can do is use this to actually figure out what is the total momentum of each one and then average them. So in the first case, because this is down, it's going to be negative d, and then everything else is going to be positive, 2d, 3d, 4d, and that gets us 8d. Here it's the second one that's down, so everything's going to be positive but the 2d. Sorry, that's a typo. That should be a minus 2d. Pretty sure I did the math right anyway. Here the 3d is going to be minus, getting us a total of 4d, and then here the last one's going to be minus, so gets us 2d. So when I average all those numbers up, I end up getting 5d as the average dipole moment for the ensemble. All right, so that's pretty much what this is. Of course, you can only really do this when you have small numbers because it pretty much requires you to do everything by hand, writing up the whole process. All right, now this leads us into a discussion about most probable configuration. Now, what we're going to say is we have two systems. So the two systems, S1 and S2, we're going to say that they're in thermal contact with each other, meaning that only heat and only energy is actually able to transfer between the two systems. So a good example of something that's in thermal contact would actually just be something like a spoon, a hot spoon in cold water. You know, there's no particles being transferred between them, but there is heat energy being transferred. And we're going to say that system 1 has an energy of U1, N1, and spin excess of 2S1, and then same thing for the second system. Now, what's going to end up happening is while energy is being transferred, things like U and the spin excess, they're going to change, but the number of particles is not going to change. We'll actually talk about the case where the particles also does change as well. And what we're going to try and think about is what is the most likely configuration that these two systems are going to go towards. All right. Now, even though the values of the two systems are going to change, they're still going to be constrained that the total energy and the total half spin excess should still remain the same. So if originally the numbers were 1 and 3, just to make life easy, um, it could end up becoming 2 and 2 or 3 and 1. Either way, it still has to add up to the same number. All right, so that's pretty much what this is saying right here. All right, so if you recall from before, that when we have these spin systems, the total energy is going to be equal to this equation right here. What I can do is I can replace the half spin excess with the sum of the two systems, which will be the same with the new values of the spin systems. And like I said before, the number of particles is still constrained by the same thing, that they should add up to the same total value of n. Now, the multiplicity function of the combined system is going to be found by taking the product of the two systems individually. You can think of this yourself. Practice it again with small numbers, like having a system of 3 and 2, and you think about, well, how many total values can I get for one? How many total values can I get for the other? And then if you treat it all as one object, you'll notice that you do have to, it will end up being the product of the two individuals. So our multiplicity function is going to be looking something like this, where it's going to be the product of the multiplicity at one state times the other system. All right, so yeah, this is kind of what I said before about a system of 2 and a system of 3 will give us a total of 6 accessible states, because system 1 can have 2 states, and then for one possible state of the other one, and then 2 more for the other, and 2 more for the last one. So that's where the 6 comes in. So what we're going to say is that in order for the system to reach, while in thermal contact, energy is going to be transferred, and they're going to go towards what we call the most probable configuration, the state where it's most likely to go towards. Now, as we know, probability is based off of the number of available states for a certain setup, like a certain number of spins, over the total number. Well, we know that the most that we can get is at wherever the value is a maximum. So that's like the most probable state is whichever one has the highest number for possible accessible states. So we're going to kind of make that same claim here, that when the two systems are in this thermal contact, that the product of these multiplicities is going to have to reach some maximum value for the half spins. And we're going to show and designate the max value with having this little caret above the S1. So this is our most probable configuration, that this is going to end up being some sort of maximum. So we have, for the first state, it's going to be some max value of S1, and then for the second state, the half spin excess will be S minus this max. Now, what we're going to do is we're going to bring back the whole Gaussian form just to kind of make our lives easy. And what we see is this, that when we have it written as at some specific state, not the max yet, it's going to be equal to this term. This is just found by multiplying the two things. Now, to figure out the min and max, as we know from calculus, we have to take the derivative and then set that equal to 0. So when we take this and we take the derivative and we set it equal to 0, something like, so we're going to just simplify this, getting rid of this whole n1 and n2 and just call it g1. You know, g1 of 0 and just g1 for this one, so that it kind of looks a little bit nicer. So to make it easier for us to take the derivative, first we're just going to ln this so that we can get rid of some of these e's. Take the partial derivative with respect to s1. This whole term basically drops out because it doesn't really change. And then we're left with these exponents over here. And because we're looking for a min and a max, we know that it has to be equal to 0. So from here, we could just solve this and solve for S1 and see that we end up getting this. So these values, S1 and S2, are going to be a maximum when the ratio of S1 over N1, S2 over N2, and S over N are all equal. So this makes it very easy for us to figure out the most probable half spin excess, since a lot of the cases we're going to know what the total spin excess is in the beginning, we're going to know the total number of particles, and we're going to know the individual particles in each individual system. Now, just as a quick check, we can show that this is also this is a maximum by taking it one step further, taking the derivative once again, and then showing that the number is less than 0, and that's what we get here. All right, so bringing it back to the case, we're gonna write it like this: that this most probable configuration, the total possible states, is the maximum when this is true, and when that whole ratio being equal to each other are also true. Now we can look at what's going to happen when we start getting some distance away from the most probable, like to kind of show that this is the most likely, that the number of states is dramatically less for other cases, by adding some sort of delta or subtracting a delta to the most probable number of half spins. So when we go back here with this s squared, we just plug this in and square it, and this and square that, and we get these two equations. Plugging it back into the equation, the exponent turns into this. We can pull out the whole s1 squared. This, I believe, is one of these is supposed to be an s2. Guess this one. I'll fix it in the slides later. And then we're left with this last exponent. So this is what we had before as the max value, and then this is the deviation from the max value. We can further simplify it by saying, well, since the max value ratios are the same, this actually just drops out. So we're left with this form for the deviation. And from here we can show that, that as we get further and further away from that, the most probable case, the number will end up dropping off very dramatically. All right. So here's a question where you can kind of work on it. You can pause the video, work on this stuff, and we'll go over it in a second. All right. So we want to figure out the fractional deviation and how much of the maximum value that we have for this. So they give us the delta being 10 to the 12th, and they give us the number of atoms. So we just actually plug and chug for this. So we end up getting that the fractional deviation is going to be something like 10 to the negative 10. Using the fraction of the max value, basically the total number of states available divided by the maximum states available, is going to be equal to that deviation form with the e function. and then we could just plug the numbers into there. That's pretty much all we're doing, really. And we end up getting e to the negative 400 or 10 to the negative 174. So basically, again, goes back to the whole idea that the the peak of that max value of this most probable case is dramatically higher than all some of the other states. So that's kind of what it's saying here. Like we have 10 to the 22 atoms with only 10 to the 12th being, you know, off. That's not really a whole lot. Um, and then we can see that the difference between the total number of available states in this case versus the most probable is 10 to the 174. So, yeah, it is an extreme difference between the most probable case versus the other setups. Here's another question that you can work on. Pause the video, work on this stuff, and we'll go over in a second. All right, so here we have a particle that is going to spin and flip its spin every 10 to the negative 12 seconds, and they want us to know the configurations we could get per second. The way we're going to get A is by just looking at like I said, the unit analysis here. So we have this number of particles, and each particle can flip every second. So the number of combinations will end up being this 10 to 34 configurations per second. Um, and then what we're going to do for part B to see how many seconds to get all these configurations, we end up getting 10 to the 140 seconds. Again, unit analysis, this is the number of configurations divided by configurations per second, gets us seconds. And then we can change this as how many universes would this be, with the universe being 10 to the 18th seconds old. So once again, divide that by the 10 to the 18th, and we end up getting 10 to the 122 universes. So yeah, it will end up taking a dramatically long time for uh, any other case to pretty much occur. Again, the reason why we call it the most probable configuration, because it has so many different combinations that work with it, that it's the most likely case that a gas is going to go towards. All right, so I'm going to end the video here. We'll continue off talking about thermal equilibrium and entropy and how all this kind of relates to that. If you have any questions, please let me know, or you can ask me in our video lecture. Otherwise, I'll see you later.